channel. In our world today we are going to discuss a very special topic, rocket propulsion. And the rocket propulsion I will split it in several parts. Today we are going to see a part 1. So first I will give a little intro. What do you mean by propulsion? It is the act of changing the motion of the body. Now I will come to the theory of rocket propulsion. So thrust can be classified into two forms, that is momentum flux and the pressure difference. So momentum flux and pressure difference can be written in this form, that is thrust is a summation of thrust of momentum flux and the thrust of pressure difference between the nozzle exit pressure and the ambient pressure. The ambient pressure is also known as a back pressure. So from here you can write like this. So from the figure you can see that is PC or P naught, in some cases they write that is a chamber pressure, and AT or S star you can see here is the throat section, area of a throat section, and VE is a effective jet velocity, AE is a exit area of a nozzle, PE is a exit pressure of a nozzle. Suppose in some condition if there is PE equals to PE, and both are in optimum condition, so we can write as F equals to m dot mv. So what is m dot? Mass flow rate of a propellant. Let's come to the next, specific impulse. So what's the definition of specific impulse? The thrust developed per unit weight flow rate of the propellant. So you can write that ISP equals to F by W dot. So it can also be split as m dot VE, that is a force, and the W dot, that is wet flow rate, can be written as m dot into G. So the m dot will get cancelled and we get this, and from here we can find the unit of specific impulse is second. And this you have to remember this point, that is air breathing jet engine having a larger specific impulse than rocket. So how much is the difference? Turbojet consists of 6,000 seconds and the rocket around 200 to 400 seconds only. See this graph, you can see here this rocket having in the lying on the lowest zone, around 200 to 400 zone, and next to that rocket we have a scramjet, then after scramjet we have ramjet, then followed by turbofan with afterburner, then followed by turbofan. See this block I have given you for your reference. This you can also find in Wikipedia. Rocket engine consists of the space shuttle vacuum around 453 seconds, whereas ramjet gives around 800 seconds. Then the highest one you see is a turbofan, that is 11,700 seconds. So you better remember this some like range where they belong to. They might ask ascending order section from this part. Next comes the specific fuel consumption. So we know what is meant by specific fuel consumption, that is how you consume a fuel with respect to a unit thrust. So this for a rocket we can also write as a reciprocal of specific impulse. So SFC equals to 1 by ISV. Whose already we know the unit of specific impulse is second. So when you're giving a reciprocal, so unit is a second inverse. Now we comes to the weight flow coefficient. The ratio between the weight of the propellant and the thrust force. So it can be written as C suffix W. So what do you mean by weight of a propellant? That is W naught. It can be written as m dot into G. And thrust force can be written as F star, that is equivalent to P naught into S star. What is P naught? Chamber pressure of a rocket. S star is a area of a throat section. Next comes thrust coefficient. So what is meant by thrust coefficient? It's the ratio between the thrust and the thrust force, that is F by F star, which can be also be written as, by rearranging, F equals to CF P naught S star. This is an important formula where this formula is used for designing and rocket engine. Next comes characteristic velocity. This characteristic velocity is a ratio between the effective jet velocity and the thrust coefficient. So you can see in the formula, this is denoted as C suffix star, and by rearranging the CF value we can write as P naught S star by M naught, and from there you can find the unit is meter per second. Now I will tell you, this is independent of nozzle performance. They doesn't need any sort of nozzle performance, but indeed they need a propellant or a propulsion system under this operating condition. At which condition it is operating, that is very important for a characteristic velocity. Like I will tell you, for monopropellant or a cryogenic propellant, it varies. How? See, for monopropellant, it's around 1333 meter per second, and whereas for cryogenic propellant like liquid oxygen and liquid hydrogen, it increases around to 2360 meter per second. Now I will come to propulsive efficiency. You have to memorize this definition. It's a ratio between the propulsive power by power output. So what is meant by propulsive power is a force into velocity, or a thrust into velocity, and our power output means a kinetic energy. So from here you can write like this, that is eta P equals to twice of U by VE by 1 plus U by VE whole square. Now I will tell you as another ratio, that is speed ratio. That is nothing but flight velocity by jet velocity, that is U by E. So in place of U by E we are going to substitute the sigma, that is speed ratio. So we get as eta P equals to twice of sigma by 1 plus sigma squared. Now comes to the thermal efficiency. Now thermal efficiency, it's a ratio between the output power of the engine by the input power of the engine, which can be written as, that is E thermal equals to VE square plus U square by 2 CV. What is VE? Is an effective jet velocity, E a forward velocity or a flight velocity we can say, and CV is a heat added or a calorific value. Now comes overall efficiency. So overall efficiency is a product of propulsive efficiency and the thermal efficiency. So when you combine both in the formula here, we get as propulsive power by power input of engine. And when you substitute the values, and we get that it's a product of forward as well as a effective jet velocity by a calorific value. Now I will go for the problems. First, focus on the first problem. Spacecraft's engine ejects mass at a rate of 30 kg per second with an exhaust velocity of 3100 meter per second. The pressure at the nozzle exit is 5 kilopascal and the exit area is 0.7 meter square. Determine the thrust of the engine in kilonewton. See, in this question it carries 2 marks, and since there is no option, there is no negative mark. Now what are the things has been given in this problem? They have given the mass flow rate, that is m dot has been given, then velocity, that is exhaust velocity, VE has been given, then nozzle exit, pressure at the nozzle exit, that is PE has been given, then area, exit area has been given, that is AE has been given, and what you have to find is a thrust of our engine, that is T we have to find in terms of kilonewton. That is very important. Let's see the solution. Here is a given data which we have seen. See, in the given data, we know that F equals to m dot VE plus AE, PE minus PA. So here, since the value is not given PA, we have to take as 0. Got it? Next, substituting the value. Next step is substituting the value. We are getting the value as 96,500 Newton, but they have asked in kilonewton. So Our answer is 96.5 kilonewton. Very simple, only you need to memorize this formula and simply you need to substitute it. And you have to know that if the value is not given, simply just consider to take it as 0. Let's go to the next problem. A rocket engine produces an thrust of 1 kilonewton at a sea level, then propellant flow rate of 400 kg per second, then the specific impulse is dash in second. Now here what are things has been given? Thrust has been given and the propellant, see the unit kg per second, so m dot has been given, and what you have to find is specific impulse. Here this question carries 1 mark, and since no option, so it carries no negative mark. Let's see the solution. Here comes given data, so we have to make sure we do convert the unit correctly. So we know that what is specific impulse? ISP equals to F by W dot. So what is mean by W dot? Again we can write that M dot into G. So all the values is given. F we know, M we know, and what is the value of G? G is 9.8. So if we in the value 9.8 in the formula, we get as ISP as 255 seconds. So our answer is 255 seconds. Comes to the next problem. A rocket engine nozzle has a throat area of 18 centimeter square and a chamber pressure of 25 bar. If the specific impulse is 127.42 seconds and the rate of the flow of the propellant is 44.145 Newton second inverse, then determine the thrust coefficient in 2 decimal places. This question also carries 2 mark, and since no option carries no negative mark. So what are the given things has been over here? Here they have given the throat area. See, they have given in centimeter square and the chamber pressure is given in bar. We need to be focused about the unit, and you have to change the unit. And specific impulse has been given, rate of flow of a propellant. So what is this rate of flow? Here they see the unit here, Newton per second. So here it is not kg per second. So what is given here? Here they have given a weight flow rate of a propellant, that is nothing but a W dot. Let's see the solution. Here comes the solution. Given data, I have written all the given data, and I also have converted its unit, that is from centimeter to meter square, from bar to Newton per meter square. 1 bar is equals to 10 power 5 Newton per meter square. ISP when W dot is given. Now let's see we know this formula, that is CF. They are asked to find the thrust coefficient. So we know what is thrust coefficient? Is a ratio between the thrust per thrust force. So thrust force means P naught S star. So what can be written as further, that is F can be written as ISP W dot, because from the formula you know that is what is the formula of ISP is a ratio between the thrust per weight flow rate of a propellant. So from there you can write that F equals to ISP into W dot. Now simply you substitute the values in the above equation and we get CF equals to 1.9. And here they have asked to find for 2 decimal number. So you have to approximate the value, that is 1.25, and the answer is 1.25. And let's come to the last question of this section, part 1. In effective jet velocity of rocket is 2700 meter per second with the forward speed of 1550 meter per second. Then the propulsive efficiency. Here in this problem they have given options, so obviously it carries a negative marking. Let's see what are the things given. See, the rocket velocity, effective jet velocity has been given, that is V is given, and forward speed, that is U, has been given. So let the solution. So we know the given data. Now we know the formula. What is this propulsive efficiency? Write down the formula. then we can find the speed ratio, that is sigma equals to 1050 by 2700. We get a 0.39 value, and after that use from this formula sigma value, that is eta p equals to 2 sigma by 1 plus sigma square, and when you substitute over here, that is 0.39 square gives 0.152, and you simplify, you get as 0.68. In the question they have given in percentage. So first I will give you intro about rocket propulsion system. So what it does is it's work on its principle, accelerate and overcome the drag forces and change the flight direction. So first I will tell the 4 basic implementations of this rocket propulsion system. It the flight within the atmosphere, near the space, or planetary flight, or a sun escape. These are the 4 basic applications. And there's an intro that I'm gonna give you, like what are things available in the rocket: propellant, rocket engine, mass, empty mass, bare vehicle, etc. etc. Now I will come with a very basic nomenclature of mass ratio, a measure of efficiency of a rocket. That is a mass ratio. And what is the implementation? It's more effective rocket design require less propellant to achieve a goal and would therefore have a low mass ratio. So in other words, we can say it is a ratio between a final mass and the initial or total mass of a rocket, where small mf defines an empty mass of a vehicle or a final mass of a vehicle, whereas m naught says our initial or total mass or a takeoff mass of a rocket vehicle. Now from there we can say what is meant by the total mass or a total initial mass is equivalent to the sum of propellant mass plus a final mass of a vehicle, that is mp plus mf. Then I will use some from the given data. I found that that is inverse reciprocal of mass ratio for a single vehicle, it reaches around 20, and for the multi-stages vehicle it reaches around 200. So that is also to be required. So now this is a graph I have found it from Saturn book. Like what this graph explains, it says that when there is a reciprocal of mass ratio, that is 1 by mr. What is mr? That is the final mass by any total mass, that is mr. So but this is a graph going from 0 to around 180, and this y direction we have a maximum vehicle velocity in feet per second, and here it's an impulse. So we see that when we have an impulse around 200 seconds, what it having now very low velocity. As we increase in velocity, there is an increase in specific impulse also. So that can be obtained from this graph. Now next comes a propellant mass fraction. This having no unit. This is used for vehicle performance. What is meant by propellant mass fraction? It's a ratio between the propellant mass and the initial mass of the vehicle. So a higher the mass fraction represents the less the weight in design. So it has been focused when you are designing a rocket engine, the mass fraction should be high. So the less weight, so less amount of drag, so less the thrust will be high. So this is a propellant mass fraction. It's denoted by a letter tau, and it's I've said already the propellant mass by initial mass. So from here we can write, that is from previously we knew that m naught equals, it's a summation of propellant plus final mass. So from there we can write that mp equals to m naught minus mf. So propellant mass fraction equals to total mass minus final mass by total mass. So it can be written like this, and from there we can write like that, tau equals to 1 minus m dot r. So remember, this mass fraction is a logarithmic effect on a vehicle velocity. And also similarly like the previous one, as we can see, as we increase in the mass fraction, what happens? The efficiency, the velocity increases with respect to the specific impulse. That's what it says. So we can say that mass fraction is dependent on vehicle velocity as well as a specific impulse. Now I will come to this point, Tsiolkovsky rocket equation, or ideally it can be known as an ideal rocket equation. So first we'll see the assumptions. So this equation can be used for a single short equation, and this equation has a specific assumption that it doesn't depend on aerodynamic forces as well as gravitational forces, and there are some conditions they consider that effective exhaust velocity are to be constant, or the summation of the effective exhaust velocity has to be varied. So this is a formula of this equation, or ideal rocket equation, that is V burnout equivalent to the effective exhaust velocity into logarithmic of inverse of m dot r, that is a mass ratio. What is mass ratio? It is a final mass by a initial or total mass. So from this assumption, what you can say, that this is used for short duration burn period of, but if the duration of burning increases, what happens? It becomes less accurate. This equation becomes less accurate because of the gravity. Next comes, this equation also can be applied for orbital maneuvers. Next I will come to the basic motion of rocket. So here already have said that in this equation it doesn't consist no aerodynamic forces or no gravitational forces, so that means no drag. So now I will tell you, when you're maneuvering at a gravity free vacuum condition, when your initial velocity is 0, then we get an equation like this, it is V burnout equals to ISP into G into logarithmic of m naught by mf. So m naught by mf, it's a inverse of mass ratio, and the combination of ISP into G is equivalent to the VE, because from the definition of specific impulse we can say that VE, specific impulse, is a reciprocal of specific impulse is a specific impulse equals to a VE, that is effective velocity by gravity. So from here we can interrelate, we can exchange the VE over here, and from here, when logarithmic of 1 by mr, we can write as minus logarithmic of m dot r. Or when we need to change this logarithmic value, we can get an exponential value, and we write like this, or this is value for this, and this is a graph. Now recalling this equation, that is m naught equals to mp plus mf. So from mp equals to m naught minus mf. So from there, by dividing entire equation a common, let's take common, that is mf. So when you take mf, we get like this. So from there, recalling the value again, that is exponential of v burnout by v effective, we get as 1 by reciprocal of m dot r. This is mass ratio. So substitute the value over here. You better remember this equation, because they might ask this kind of question for 2 marks. You better remember this procedure. It is better than memorizing this formula. Similarly, instead of mf, you can, when you take a common of m naught value, you get this value. So both the values, both the expressions are important. So it's nothing like all the factors, they improve the ISP, the specific impulse. They depend on specific impulse. So as we know that by increasing specific impulse, we enhance or improve the efficiency of a rocket propulsion system. That's what they have expressed over here. Now I will come to a vertical flight. When aircraft is undergoing a vertical flight, so I will give you a few expression what happens to the velocity at a vertical flight when the initial velocity is 0. So this is an important expression. V burnout equals to ISP, the specific impulse, into gravity into logarithmic of 1 by mass ratio minus gravity into this burnout time. T suffix P is represented as burnout time of a propellant. So similarly, instead of ISP into G, we can write VE. Now we'll see at what height it can gain at the vertical flight at some particular amount of given time, burnout time. So this is a formula. This is another important formula. See how you can remember this formula. I will tell you very simple tricks. Already you know this value is our ideal equation. So when you are using ideal rocket equation and when you are using for vertical flight, we are adding up an extra term, that is minus GTP. Now when you are finding the height, what you are going to do, the same value with this inner value, you multiply with TP. See, both here also we have TP, here also we have TP. Here TP into TP squared comes. Plus we have some extra term. What is extra term? Into we have some 0.5 term, or we can say 1 by 2 GTP squared. So you may have a confusion, where is a TP square, where is a single TP. Better not to get confused. You remember this in basic equation from their vertical flight. What is happening? Minus GTP is coming for the altitude. What is happening? We are multiplying the entire equation into again T. Because you remember one more thing, why to multiply and where to multiply, that also might get confused. Remember the unit. What is the unit for velocity? Per second. But whereas for altitude, the unit is meter. So from velocity, how we can convert into a meter? By multiplying the second, because meter per second into second, when you multiply, you get meter. So of course, for the velocity, you need to multiply the time, that is time of burnout, and so we get this altitude here, and that's it. And the thing you remember here, the coefficient you need to put as 0.5 or rather 1 by 2. That's how you can easily memorize the formula. Now I will tell you the effect of propulsion system on a vehicle performance. These are the basic parameters, that is specific impulse, mass ratio, the burning time, or this aerodynamic lift, or you can say how the gravitational force is accounted into the system, or a drag force is accounted into the system. These are the 4 basic points, and apart from that there are a lot of other points, but these are the 4 basic points. Now comes on multistaging. So first let me tell you what is meant by multistaging vehicle. The multistage or a multistaging vehicle permits a higher vehicle velocity, more payload, so more enhance the long range of a missile or long range of a ballistic performance. So now I will tell you, we have around 4 types of multistaging. You can see here, one is a staging, second one is a partial staging, third one is a parallel staging, and the fourth one is a piggyback staging. By seeing the figure, you can identify that what is in the series, the one after another, the sub-rockets are placed, one after the other. Next comes a partial staging. So partial staging is a combination of a series as well as a parallel. So you can see the figure. Now I have no need to tell like what is mean by a parallel staging. Parallel staging, it's getting attached along the stages. See, it's getting along the stages. And what is meant by piggyback? You know, someone when you're a kid, somebody might be carrying you behind your back. So same thing, just the space shuttle. This is a main rocket. Somebody is picking back to the another stage. That is meant by a piggyback stage. Now, difference between parallel and series staging. So this is a figure. So from here you can understand that is before ejecting or after ejecting how they deflected. Now let me explain you about this basic staging of rockets. So see in this figure there are consist of two stages and sub-rockets. What is meant by stages? See here to here one stage and here to here another stage, and beyond this we call as a payload. Okay, see here what is meant by stage? When this is one system, this is another system, and this is payload. Okay. Now what is meant by first? What is meant by sub-rocket? This is one sub-rocket when it consists of the air system. When this part, the stage 1 ejects out, the remaining one, this second stage and the payload will say as a second sub-rocket. That what is mean. So I have explained over here that is first sub-rocket is a complete rocket vehicle, and the second sub-rocket is a first one sub-rocket minus the first stage. That is the first sub-rocket, the entire one minus this one. So you get this remaining, that is a second sub-stage. So what is mean by M0, MP and MI, MF? Already you know that what is initial, then propellant, initial, final, this and that. Now here I will tell you a very important topic, another important topic. This another few more ratios you need to focus when you focus on the multi-staging, that is payload, propellant ratio, structure ratio. Already have studied. One more ratio is a mass ratio, and how all those ratios are interconnected with each other. Now what is meant by payload ratio? Already, let me recall you what is a mass ratio. Mass ratio is a final mass by total mass or an initial mass. So but here, so already you see always the total mass is on the denominator. Okay, so that you keep in mind, always the total mass is the denominator and which having the highest value compared to others, and similarly always in all those ratios what happens, the final the total ratio or the initial total mass or initial mass will be in the denominator for all the factors, and the propellant mass, suppose I am keeping a payload ratio, that means the mass of a payload will be in the numerator, and denominator what will be there in the total mass or an initial mass. Let's see the formulas. First focus on the payload ratio. So payload ratio is a ratio between the payload mass and the initial mass of a rocket. Here comes a formula, you see, it denoted by the letter lambda, notation by lambda or symbolized by lambda, which is a ratio between MPL, payload, by the total mass. Similarly, propellant ratio already have studied, that is MP by M0, that is a ratio between the propellant mass by total mass, initial mass. And then comes a structural ratio. Structural ratio is a mass of a structure by the mass of a total vehicle. Now I will tell you how this basic this ratios, how they are interconnected. Now what is phi? Phi is a propellant ratio. Propellant ratio is connected with a payload and structure. That is 1 minus payload and 1 minus a structure ratio. And after, in other way, what do you know? What is MR? How MR and phi is related? That is phi. Phi is nothing. Phi or tau, in some book they have written phi, some book they have written tau. Its thing is the matter, you remember the matter, how they are connected. So what is mass ratio is equivalent to the 1 minus of propellant ratio. So once you know that, so you can write in other way that 1 minus of epsilon bracket 1 minus of lambda, or you can write in this way. You better remember this. Sometimes they might ask MCQ from this basic formula. They ask to find a suitable question or a suitable answer among the options. Now I will skip for the problems. So for a vehicle in a gravitational-less space, determine the mass ratio necessary to boost the vehicle velocity by 1600 meter per second when the effective exhaust velocity is 2000 meter per second in 2 decimal places. So what are the things has been given over here is a vehicle velocity and the exhaust velocity, that is a burnout velocity, and the VE value has been given, and what we need to find is a mass ratio. So here comes a given data, and let's recall this formula. This formula already we have checked out, and there's nothing to do much in it. You know this formula and apply, substitute the values in this equation, and you get this, what is the value of MR. MR is around 0.459. So that's all is our answer, required answer, because I have written 0.46 because they have asked in 2 decimal number. So make sure of this. Sometimes at what decimal number they're asking. If they're asking on 1 decimal number, what will be your answer? Your answer will be 0.5, because after 0.46 we have to write as 0.5 in 1 decimal number. Since they have asked in 2 decimal number, I have written as 0.46. Okay, let's go to the next problem. What is a mass ratio? MP by M0 for a vehicle has a 1/5 its original takeoff mass at the time of completion of rocket operation in 2 decimal places. So what we have given is a MP by M0, that is a propellant ratio has been given as a ratio of 1/5, that is 1/5. So see the solution here, given data is given. So we know the basic fundamental formula, that is M0 equals to MP by plus MF. So from there we can write that MP equals to M0 minus MF. Dividing the entire equation with M0, so we get this equation, and already what is our given data? MP by M0 has been given, and we need to find MF by M0. So very simple. We have only thing is you need to remember the formula. So as we get as answer, that's it.
One more thing here, they have asked for 2 decimal number, so it's better when you're typing it in your keyboard is 0.80. That is very important for to write down. Don't write 0.8, they might deduct that value. Better to write 0.80. Comes to the next question. A rocket engine produces an effective velocity of 2200 meter per second for a dragless projectile with burning time of 5 seconds and propellant ratio 0.57. Then the burnout velocity will be kilometer per second in 2 decimal places. So what are the given data? So effective velocity is VE, burning time, that is TP, and propellant ratio is either you can write tau or phi, or we can write MP by M0, and we have to find the burnout velocity. See here, what they have asked is a projectile. You underline these terms, and also they have given a burnout time. This is the given data. So you have to use, in this case, you have to use this formula. Why? Because they have asked a word called projectile. When you see in a question a word called projectile, you have to use this formula, that is a vertical flight formula. It's nothing much. You have all the given known data. Here they have given MP by M naught they have given. What you need is MR. You know the relation between this MP by M naught and R relation. From there you can find this MR value. Then substitute in the first equation and you get the 1815.28 meter per second. But in the question they have asked in terms of kilometer per second. So divided by 1000, so we get 1.82 kilometer per second. So be specific with the units. If asking this nanoseconds or kilometer to meter conversion, make sure of it. Come to this next question, or a vertical rocket trajectory projectile and effective velocity of 2120 meter per second with a burning time of 10 seconds and mass ratio 0.6. Then the burnout altitude is in kilometer into decimal places. So what they have asked here they have given effective velocity has been given 2120 meter per second, burning time 10 seconds, mass ratio 0.6, and here they have asked burning altitude. So here previous question we have found burning velocity, burnout velocity. Here they have asked altitude, and one more thing, it's a trajectory projectile is given. So you know that which formula will be used. This formula will be used. Now you simple, all the things are given known to you. We substitute the value and we get in meter. So burnout altitude you get as 10.34 kilometer. So answer is 10.34 kilometer. Come to the last question of this section. A single stage rocket engine produced with structural ratio of 0.4 and the payload of 0.6, then the propellant ratio will be. These are the given datas. It's a very simple question. It's a one-mark question. You just really need to know this formula, correct formula. So you have to memorize those formulas and you substitute the values into the formula